Good afternoon, everybody. I am MAKIAN Masoud from Iran. I study in South Korea. My presentation today is about ammonia fermentation, high-rate ammonia fermentation using an upflow anaerobic digestion. First, I want to discuss about the importance of ammonia. Ammonia is very highly produced with a market size value of $74 billion per year. Its application is mainly for fertilizers, but there has been an increasing demand to use ammonia as a hydrogen carrier because it has a higher energy density and it's easier to liquefy compared to the hydrogen. Also, when we are storing ammonia, it's much more safer than hydrogen. So it's increasing demand to use ammonia instead of hydrogen storage. Traditionally, ammonia is produced through the hyperwash process. 96% of the current ammonia is produced during this process, which heavily relies on the fossil fuels, mainly CNG. When we get the hydrogen from the fossil fuels, and then when we combine it with the nitrogen, we can get the ammonia. But this process have a very huge impact on the greenhouse gas emissions, and also it costs a lot. Another alternative to produce ammonia is through the anaerobic digestion. Usually, when organic waste is degraded through anaerobic digestion, it contains organic nitrogen, which can easily convert it to ammonia. But at anaerobic digestion, if we want to heavily rely on just anaerobic digestion, we can get a very low amount of ammonia, and because the anaerobic digestion has very long HRT, so the production of ammonia through just anaerobic digestion would be very limited. Ammonia fermentation is considered as digestion of organic nitrogen waste into ammonia under anaerobic digestion. The difference between the ammonia fermentation and anaerobic digestion would be low HRT and higher pH in ammonia fermentation. The low HRT will help us to achieve higher rate of ammonia production. We can get these organic waste that are high in nitrogen content from slaughterhouse waste, digested sludge, or even chicken manure. Up to 50% nitrogen content can be obtained from organic wastes. In this study, we had three objectives. The first one, to achieve the highest ammonia concentration that can be achieved through anaerobic digestion. And we wanted to maximize production rate. Thus, we used the upflow reactor to increase the production rate. Thirdly, we wanted to investigate what are the benefits of having a high concentrated ammonia concentration during anaerobic digestion. And we used an upflow reactor. We used gelatin as a substrate with nitrogen content between 1.4 to 21 gram nitrogen per liter and the HRT of 8 hours, which is very low compared to conventional anaerobic digestion. It can be more than 20 days, up to maybe 60 days. And the condition was mesophilic in this reactor. We used the gelatin as a simple source for the protein substrate, so we wanted to also consider how the degradation happens and where are the limitations in ammonia fermentation. These are the results of our research. So we gradually increased the gelatin concentration at the fixed HRT of 8 hours. We could reach up to 12 grams per liter of ammonia, which was very high compared to the conventional anaerobic digestion, which can be between 1 or 5 grams nitrogen per liter. Previous studies that studied the ammonia fermentation, they could achieve up to 9 grams per liter, which was from chicken manure. The importance of having this high concentration of ammonia is that during the ammonia stripping that we can obtain the ammonia from the digestate is that with the same energy during the ammonia stripping, we can get a higher amount of ammonia, which will have less energy requirement, and thus we can save money when we have higher concentration. The next step after achieving the high concentrated ammonia and also production rate of 36 gram nitrogen per liter, we wanted to know how high efficient ammonia fermentation can be achieved. Later we did batch ammonia fermentations. During the upflow reactor, we obtained granules, and these granules were very well formed. So we wanted to know if the formation of granules had impact on the high ammonia resistance. So we crushed some of the granules, and we compared the performance with the intact granules, but we didn't see any difference in ammonia production at high ammonia concentration of 10 gram per liter. Later, we changed the SI ratio, substrate to inocular ratio, to see if we have a higher amount of inocula, it can be achieved higher ammonia concentration, but also we didn't see any difference between different SI ratios. Later, we did a test between the granules taken at different stages of the USB reactor, where we observed that the granules formed at the later stage of the reactor had higher performance compared to the stages prior to that. We could conclude that the adaptation of the microbes to ammonia can lead to their high resistance to the ammonia. The high resistance to ammonia can lead to production of higher ammonia concentration. Later, we did the microbial analysis. So the top 4 microbes were protein degrading bacteria. The first one, Hathewaya, has been previously shown to be gelatin degrading bacteria, but their performance at a high ammonia concentration of 12 gram per liter has not been reported. Also, Clostridium was the second microbe that we observed. The concentration of 12 gram per liter can be very lethal to all the microbes, but during ammonia fermentation, when we gradually increase the gelatin concentration, that will lead to gradual increase in ammonia concentration, can make adaptation to the microbes. So the first reason that we had high concentration was the adaptation of microbes. And also, the high rate can be achieved through the upflow reactor. Later, we wanted to see the mechanism, how the ammonia is produced. As you may know, that organic nitrogen can be hydrolyzed to amino acids, and then later it will deaminate to ammonia and organic acids and the VFAs. So we measured the amino acid concentration in some stages of the reactor, and from knowing the concentration of amino acid, we could understand the deamination and hydrolysis rates in each step of the reactor operation. We could observe that the rate limiting step in ammonia fermentation would be the deamination. Deamination means that amino acid conversion to ammonia when the organic nitrogen converts to ammonia, and other products such as alcohols or organic acid can be produced. So rate limiting step during our experiment was the deamination, and we suspected that there might be 2 reasons why we couldn't achieve higher concentration than 12. One of the reasons we want to explore later is that is it because the amino acid accumulation or a high ammonia concentration can inhibit the microbes so they cannot deaminate the amino acids. So during this study, we could achieve high ammonia concentration of 12 grams per liter, high production of ammonia, 36 grams nitrogen per liter. During this study, when we increased the gelatin concentration, in case of COD concentration, we used up to 120 grams COD per liter. 120 grams COD is very lethal when we want to have methane production. But we didn't see any difference in the performance. In case of organic loading rate, it would be around 450 grams COD per liter per day. It is very huge. We tested, but there was no drop in the performance. We could see that at 450 grams COD per liter per day, there was no increase in ammonia concentration, but there was still 12 grams per nitrogen per liter was produced without pH drop. Also, we showed that if we have high ammonia concentration in the effluent, we could get higher ammonia with the same energy input. Also, during batch experiments, we could conclude that the reason behind high performance was the adaptation of the microbes to the high ammonia concentration. And later in the amino acid analysis, we could conclude that the rate limiting step during ammonia fermentation is the deamination step. Future work would be ammonia fermentation plus ammonia stripping and then getting higher methane because, as you know, ammonia is the inhibitory during anaerobic digestion when we want, for methanogens, when we want to get methane. We want to investigate the relationship between ammonia fermentation and the VFA production, and also there should be studies that why the deamination failure happens during the ammonia fermentation. And thank you for attention.